Okay, hello. My name is Chris, and I am a PhD student in the Hetsys Centre for Doctoral Training at the University of Warwick. And this is part of our Computational Toolkit seminar series on an introduction to high-performance computing. So I'm going to talk very broadly about what high-performance computing is and what's involved, and hopefully give you a bit of a flavour of the kind of research that a computational scientist does. Okay, so let's think about the origins of what we're doing here, really, as a computational scientist. So if you go back 100 years or so and further, you didn't have the option of doing any kind of computer simulation, really. So science, and I'm talking really from the perspective of physics because I'm a physicist. Science had kind of two main streams, ways of approaching problems. You either had theory or you had experiment. So I've got two pictures here. One is a theorist working on a blackboard, and the other is Galileo, or a representation of Galileo dropping his two objects and seeing if they fall at the same rate. And really the crucial point I want to get across. Okay, so experiment, you can always do an experiment. You think of some theory, you want to test it. And you can go away and come up with a clever experiment to test that. But the point I want to make about theory is that really theorists were limited to what they could come up with, what we would say analytically. Could they write down a solution to the problem? Or could they write down something close enough to the solution that they can actually just, with pencil and paper, get a number out? And actually, there aren't very many, there are very specific cases where that is possible in physics, but actually most of the problems we're interested in are too complicated. The solution can't be written down simply or easily with pencil and paper. So that's kind of where the computer comes in, where computational science comes in. So yeah, so why computational science? Well, it's as I sort of hinted at, it sits somewhere between the traditional disciplines of kind of experiment, where you're physically doing things, and theory, where you're just thinking and coming up with elegant solutions. So we have these days a vast array of methods, techniques, algorithms that can solve problems or simulate problems that just wouldn't be possible by hand. So I've got a picture here of, I think this is a NASA computational fluid dynamics simulation modeling airflow around the space shuttle on re-entry. Now, there's no way that you'd ever be able to write down that solution by hand. It'll be turbulent, it'll be complicated. But using numerical simulations, using a powerful computer, you can predict the nature of fluid flow around that aircraft, and potentially you can learn useful things like, well, where is it going to get hottest? Where are the forces on the aircraft biggest, and so on. So yeah, we provide this crucial link. So really, okay, a theorist still has to write down the equations that we're going to solve. We still have to know what equations we're going to solve, but the computer enables us to solve them without ever having to write down the solution in a simple form like you would pencil and paper in a maths class. And then beyond that, these days we also move into what we call predictive modeling, where really we're looking to go where the experiment cannot or has not. So I work in the field of materials science, and one of the big goals of my PhD really is in actually predicting candidate materials for experimentalists to look at. So maybe we run some simulations and we say, well, I'm interested in permanent magnets largely, and we say, well, we actually think this would be, we run some simulations and we say this would be a good permanent magnet. The idea is that we can provide some predictions, and then the experimentalists can go away and work on it. So okay, so that's what computational science is about. So why high performance computing here? I've got a picture of a representation of Deep Thought from the Hitchhiker's Guide to the Galaxy, which was a famous, very powerful computer. So why high performance computing? Well, real physical systems are immensely complicated. You're talking about millions of atoms. You're talking about in the context of my work, tens, hundreds of electrons, and it's all very complicated. And so calculations take a long time. You have an algorithm, but it's still going to take you a long time and a lot of computational resources to solve those problems. So to make it feasible, we use very powerful computers. So we use computers that can perform much more complicated and much more complicated and demanding tasks than your average personal computer. Okay, so that's kind of the motivation in the background. So what is high performance computing? Well, it's about computers that are powerful, that deliver high performance. So I've just thought of a few maybe metrics here. So how powerful is my computer? So really the most important aspect in terms of computing power for any computer is the number of cores it has available. So how many individual processors does the computer have available to it? Now, obviously, different processors run at slightly different speeds, but it's a good metric, and most modern processors are pretty comparable. So, on a typical laptop, I went on a retailer's website yesterday when I was putting this presentation together. A typical laptop these days, if you went out and spent a few £100 on a laptop, you'd get something with probably 4 cores on it. Okay, so 4 compute cores. Now, the high performance computing facility at Warwick, the flagship machine is a machine called Avon. And on that machine, we have 9,528 cores available. We don't necessarily use all of those all of the time, but that in principle is the number of cores which are available. So, you know, you've gone from 4 to almost 10,000 cores just for a local computing facility here at Warwick. The UK national supercomputer, now I do have a colleague actually who runs simulations on this supercomputer. This is called Archer 2. It's based up in Edinburgh. Now Archer 2 has around 750,000 cores. Okay, so already, you know, already 75 times as many as the local Warwick machine. And then for a bit of fun, I said, well, what's the most powerful supercomputer in the world? At the moment, it's a machine called Fugaku, I believe I'm pronouncing that correctly, in Japan. And that has over 7 million cores, so almost 10 times as many cores as Archer does. So to give you an idea, you know, if one processor is taking maybe, in principle, you know, in an ideal world, if you had one processor and it was taking you 750,000 hours to solve a problem, which is just not feasible, you know, that's a ridiculous amount of time. We wouldn't be interested in the answer by the time the calculation finished. Archer 2 would be able to solve that problem ideally in an hour, probably a bit more than that for complicated reasons, but that's the idea, is if you've got just a complicated numerical thing that needs to be done, the more cores you can throw at it, the quicker you'll get the answer. Then we also need to think about data storage. So if we're not running a big simulation, we need to store all of that data that the simulation is generating. So this typical laptop that I found, 512 gigabytes of storage, which is a lot. You know, when I was a kid, that was a massive amount of storage. So, you know, people are familiar with mobile phones these days have sort of 64, maybe 128 gigabytes of storage. Some people have more, some people have less. So Warwick's Avon facility that I mentioned just now, that has 1 petabyte of storage available, roughly. Now a petabyte is 1,024 terabytes. So there are 1,024 gigabytes in a terabyte, and there are 1,024 terabytes in a petabyte. So already we're talking, you know, 2,000 times as much storage as your typical laptop. The UK national supercomputer, this scales a bit like the compute cores do. So the UK national supercomputer has over 15 petabytes of storage. And then Fugaku in Japan, I looked that up, and they claim they have over 150 petabytes of storage. So, you know, when you're running these big simulations, solving big problems, you need to store the data, and this is the storage that's available on some of these facilities. And then finally, there are some other aspects that you think about. So if you've heard of machine learning is a really big topic these days in lots of areas of computational science. And for machine learning, typically most codes are written to use what we call a GPU. So the process, the core count I was talking about was all about CPUs, central processing units. And what they are good at is they're good at performing quite complicated operations. Well, a GPU, so a CPU typically has a few cores, but the cores are all very smart, so they can do lots of operations. Well, a GPU is the other way around. A GPU typically has lots of cores, so maybe hundreds of cores on a single unit, but those cores are not very smart. They can do simple operations quickly, but they can't do the intelligent stuff. But for certain applications, GPUs are immensely powerful. So as I say, machine learning is an area where GPUs are used a lot. I know certainly that there are lots of big physics codes these days that are moving to being GPU accelerated, because there are some there are some problems that the GPU suits very well. So often an HPC facility has all of these cores, all of this storage, and so on, and then in addition, they'll have GPUs available for people who need to run simulations that require those. And then you also need to think about how much RAM you need. So okay, you've got a compute core, you've got data storage, but actually when the computer is working on the data, it pulls it into RAM, random access memory. Now Archer 2, I didn't mention this before, so I said Archer 2 has 750,000 cores. Well, a supercomputer is kind of a complicated beast, because actually it doesn't have 750,000 cores all in one place. It's divided into what they call compute nodes that can talk to each other. And typically you might have, I imagine, I don't have the number off the top of my head, but I imagine Archer 2 probably has something like 100 cores per node. And each node has to have a certain amount of RAM to store the data that the computer is currently working on. And for Archer 2, this is between 256 and 512 gigabytes per node, which is a lot. So a typical laptop these days, maybe 8 gigabytes, 16 gigabytes of RAM if you're lucky. So, you know, these machines can work on a lot of data all at once, which is really important when you're running big simulations where there is a lot of data to crunch. Okay, so that's kind of like what high performance computing is maybe about. These are why these computers are high performance. So then I wanted to talk a little bit about, well, what kind of software do you run, right? Because when you use an HPC facility, I hate to break it to you, but you don't log in and it's running, you know, Windows, and you open Microsoft Word and type a document up. That's not quite how this works. So first up, what operating system do you use? Well, pretty much all HPC facilities run a version of what we would call Linux. So a Unix or a Unix-like operating system. Linux is a Unix-like operating system. There are distinctions, but these are systems that allow for a bit more flexibility in terms of code development and running of code and so on. So typically what happens when you log into one of these systems, and I've got a picture here, you just have a terminal output, right? So you just have this black screen with kind of a flashing cursor. There's no mouse that you can use. There's no GUI, a graphical user interface like you're used to on a laptop. You have to type commands, so you have to know what these commands are to be able to navigate the files and run the things you're looking to run. So yeah, I've got this picture here. So this is me logging into. I've blurred out usernames and things, but this is me logging into one of the Warwick clusters. So this isn't Avon that I mentioned. This is a cluster that I use called ORAC, which is slightly older, but I don't need hugely powerful. I do sort of medium performance computing, if you want to think about it that way. I'm logged into a machine, my laptop, and then I will jump to a machine on the Warwick network, and then from the Warwick network, which is secure, I can jump to ORAC and start running jobs. And this is what it looks like, you know. And if you're interested in this sort of thing, when you log in, you log into a login node, and they don't like you to run calculations there. You have to actually submit them to a queue. But anyway, so that's kind of the operating system. It's Unix or Unix-like. So you can imagine this command line where you can start typing commands. Okay, and then what software am I going to use? Well, you have to ask yourself the question, what problem am I looking to solve? Because we're looking to run a very specific type of simulation, generally speaking. There's a particular material or problem that we want to model. And most codes are written to tackle a very specific type of problem. So I've got a few examples from physics and the physical sciences here. So CASTEP is a very well-known code, particularly in the United Kingdom. CASTEP, I don't remember what all of these abbreviations stand for, but CASTEP models electrons in some sense around atoms and enables you to understand energies and forces on molecules and big systems. loosely. And so CASTEP is what we call a density functional theory code, and density functional theory is just how it works out what the electrons are doing. I've got another example here, lamps. So lamps, again, it's something that's massively parallel, I think, is one of the MPs, I can't remember. But lamps is what we call a molecular dynamics code. One of the other M's is probably molecular. So lamps doesn't model electrons, lamps models particles bouncing off each other in some sense. So it works at a slightly larger scale. But if you wanted to model, say, a little box of gas, lamps might be a way of doing that. I've picked another example. So Epoch is a code that's actually developed at Warwick. Epoch is a plasma physics code, and I don't have a logo for it, but it's a code that's used to model the physics of charged particles in plasmas. And then I've got another example here, OpenFoam, which is a fluid dynamics code. Okay, so this is for modeling fluid flow, maybe around, an aircraft, like we had that picture earlier on. And so you have to pick a code, and that or piece of software. So I should mention perhaps that when we talk about software, we typically say a code because we're talking about a specific code for solving a specific problem or class of problem. Okay, so once you've picked your code, how do you use it? Well, what does it look like to run? So typically, actually, again, there's very rarely is there a graphical user interface. So more often than not, you prepare an input file for the code, which is some kind of text file that the code will read in. You either prepare this by hand, or typically maybe there's a little piece of software that will help you prepare it. And that has all of the parameters that the code takes in and tells it what problem to simulate. So you prepare an input file, and then you have to use a queuing system because there are typically lots of people looking to use these facilities. So what you'll do is you'll prepare your input file, and you'll prepare a little what we call a script. And what that does is, and then you submit the script to the queue, and the script says, I would like this many compute cores, I would like this much memory, and I would like it for this long. And then here's the calculation I want you to run with that. And it goes into a queue, and you can watch your job as it moves through the queue, and then eventually it will run. And when it runs, what happens? Well, do you see anything happening? Typically not. Typically, I will submit jobs to a queue and then go off and do some other work, make a cup of coffee, whatever, depending on how long I think the job is going to run and how busy the queue is. And so what typically happens is the code will run and it will dump a whole load of data to some output files. And these output files often contain raw data. I mean, some of the codes I work with dump data to binary format, which just means nothing. So you have to then take these output files and do some analysis on them. So it's very alien to people who are used to working with kind of interactive pieces of software with graphical interfaces all the time. But it's just a very efficient way of doing it. Although we've got very powerful computers, the problems we're looking to solve are very big. So we want minimal overhead. We don't want to be running unnecessary things. And also from a software development point of view, it's much easier to write a code that just takes in an input file. Okay, maybe it takes a bit more getting used to for the user, but as a software developer, as a scientist writing the code that models these systems, I don't need to faff around with all of the hassle of making a user interface. I can just say, okay, here's the input file, here are the parameters you need, and it makes my life a little bit easier as a developer. So I've just got right at the bottom here, this is an example of, so I use a code called Hetsys, which is a fairly niche density functional theory code, but it models the physics of alloys and magnetic systems primarily, which is the physics that I work on. And this is kind of what an input file for Hetsys looks like. So there's a job which tells it exactly what kind of problem it's running. So 3 means three-dimensional. O2 means, if you're a physicist, it means a density of states calculation. Then it has things like telling it has some description of if you're a physicist, again, it has a description of where the atoms are sitting and so on. And then I can't scroll down in this presentation, but if I scroll down further, it has a lot of options specifying how the calculation should be done and what parameters I should use, how much accuracy do I want, and so on. So Hetsys will take in that input file, I'll submit a batch script, and then it will produce a load of output data that I then analyze. Okay, so that's what a code looks like to run. I then just thought briefly, kind of to wrap up the introduction, I talk about some of the challenges that software developers face. So I've talked about this idea that you've got lots of compute cores, but how do you use them? How do you make best use of all of those? Because if you've ever written any code, typically, you'll write some Python code is one of the really common languages. If you write some Python code on your laptop, generally speaking, it's running in serial. So it means it's running on one core. And worse than that, it's not generally running hugely efficiently. It'll be pretty fast if you're doing low-level stuff, but Python as a language is very flexible, but it's not all that fast. So the first thing is that generally speaking, software for high-performance computers is written in what we call low-level languages. So languages like C, C++, and Fortran are the three big kind of examples, which are languages that are a little more what we would say verbose, so that there's a little bit more code written compared to Python. But the advantage is that they tell the computer quite specifically what it needs to do, which means the computer has to do less thinking about what it's got to do and more doing, in some sense, compared to a language like Python, which means it runs a little bit faster, which is good for us because the resources are limited and we want the code to run as quickly as possible so we can run the best simulation that we can. Beyond that, then, you've got things like code optimization. Okay, so you can write code that wastes a lot of compute time. You want to make sure that you're not repeatedly calculating quantities. You want to make sure that if you have a big array that you need to look at all of the elements of, you want to make sure that you're looking at those elements in the right order so the computer does it most efficiently. There are all sorts of challenges, and code optimization is a big part of kind of scientific software development, because when we would like the code to be right. First off, we want it to solve the right problem, but we want it to do that pretty quickly. So optimization is a big challenge. And then once your code is well optimized, the next step is to parallelize it. So I said, okay, your typical Python code is going to run in serial, one processor. Parallelization is all about employing multiple processors, and that's actually an immensely complicated topic, because, as I mentioned earlier, this idea that a big supercomputer is split into lots of nodes, right? Lots of different smaller, if you like, computers that can all talk to each other. Well, as a software developer, you have to control the talking to each other that these things do, and you have to decide, okay, which bits of data need to be passed around between all of the processes, which bits of data definitely shouldn't be passed around, which bits of data need to be communicated a lot, not so much. And so parallelization is a massive topic, and there are a few kind of schemes for doing this. But so yeah, okay, so you have to pick the right language. You have to make sure the code is kind of well optimized, it's doing things efficiently, or fairly efficiently at least, and then you have to parallelize it. So you have to make it so it can run on these many thousands of cores, and it's a non-trivial task. Parallel, and it gets worse the more cores you want to use, because when you want to use lots and lots of cores, your parallelization has to be very, very good. Otherwise, all of the processors talking to each other can take more time than more time than solving the problem itself, kind of thing. So yeah, so it's a big topic, and so I just thought I'd mention briefly some of the schemes. So I've mentioned the idea of these nodes, okay, so they need to talk to each other, and that's this idea of distributed memory parallelization, where actually data is stored in lots of different locations, and you have to manually communicate data between little tasks, little parts of the calculation. Before that, really, there's a model which is shared memory parallelization, which is like on your laptop, say, where you've got 4 cores, but they all access the same bit of memory from the computer, and that means that actually there's less communication. They can all work on the same piece of data. You just have to make sure that they're not working you just have to make sure that they're working on different bits, different parts of the same chunk of data, loosely. And then there's also, I mentioned GPUs earlier. There's also GPU acceleration, and using a GPU is not as simple as saying, yeah, okay, run this piece of code on the GPU. You have to do a lot of thinking about how you're going to port your code, move your code across so it'll work on a GPU. You have to do, because you have to initially kind of prepare some data, and then maybe you'll say, okay, this part of the calculation can be done on the GPU, So you send it across and you ask for the GPU to do it, and then you have to pull across data back from the GPU and analyze it. So yeah, parallelization is a huge topic. I mean, you know, I certainly can't cover all of it. There's an entire lecture course at Warwick in 4th year that, and even that would only claim to kind of skim the surface of this topic. So it's big and it's complicated, but it's very exciting, and it does enable us to do immensely complicated calculations. So yeah, okay. So shared memory parallelization. The most commonly used scheme is MPI, the message passing interface. Sorry, that's distributed memory. Distributed memory parallelization, that's MPI. Shared memory parallelization, that's one of the schemes is known as OpenMP. And then GPU acceleration, NVIDIA have a sort of an environment, I guess you'd call it, or a package called CUDA, which is about using their GPUs to accelerate tasks. So there are lots of options out there for parallelization. Yeah, so I think really now I've probably covered just about everything that I wanted to cover in an introductory topic. So we've talked a little bit about the motivation for computational science, this idea, the motivation for computational science as a whole, and then also the motivation for using high performance computers because the problems are complicated. We've talked a little bit about what a high performance computer is. So this idea that it is really just a very big computer with, you know, many thousands of cores, much more storage, and what, you know, and the ability therefore to process much more information. And then we've talked a little bit about actually how you would use that. So what it looks like to log into a high performance computer, what it looks like to run software on that computer, and even how you would develop that software. So yeah, I think that just about wraps up everything that I wanted to say. So all it remains for me to say really is to say thank you very much for your attention, and I hope you enjoyed the talk.